Look up. In any major city at any given time you'll see them. Silent, skeletal figures silhouetted against the sky. They are the temporary architects of our world. The steel giants that piece together our skylines, block by heavy block. We see construction cranes so often they almost become invisible, a static part of the urban landscape. But have you ever really stopped and looked at one? Have you ever truly wondered, how? How does a machine that weighs hundreds of tons, stretching 1,000 feet into the air, not just fall over? And even more baffling, how did it get up there in the first place? In the next 15 minutes, we're going to unravel the astonishing story of the construction crane. It's a story that begins thousands of years ago with ropes and wood and leads to one of the most ingenious and counterintuitive pieces of machinery ever invented. We'll explore the beautiful simplicity of their physics, the mind-bending complexity of how they build themselves, and the terrifying consequences when these gentle giants fail. This isn't just about a machine, it's about humanity's relentless ambition to build higher. Our story begins not with steel and motors, but with muscle, wood, and the birth of a revolutionary idea in ancient Greece. Before cranes, building anything monumental, like the pyramids, required immense brute force. Tens of thousands of laborers dragging massive stones up enormous earthen ramps. It was effective, but incredibly inefficient. The Greeks, with their obsession for mathematics and mechanics, knew there had to be a better way. They developed a device called the trispastos, or three-pulley crane. Using a system of ropes and pulleys, a single person could lift an object many times their own weight. It was a game changer. The Romans, masters of engineering and conquest, took this Greek ingenuity and scaled it up. They created the polyspastos, a massive, human-powered crane. Its centerpiece was a huge treadmill, a wooden wheel, sometimes 15 feet in diameter, where multiple men would walk, the combined weight turning a winch that hoisted colossal blocks of marble into place. It was this machine, smelling of wood and human sweat, that built the Colosseum and the aqueducts that still stand today. These ancient machines established the fundamental principles of mechanical advantage and leverage that, incredibly, still govern the titans of our modern skyline. For over 1,000 years, the basic design of the crane barely changed. They were powered by men, horses, or donkeys, and were limited by the strength of their wooden frames and hemp ropes. But then, two things happened that would forever alter the course of construction: steam and steel. The Industrial Revolution wasn't just about factories and trains. It was about power. Suddenly, the tireless, immense strength of a steam engine could be harnessed to a winch. Simultaneously, the development of cheap, high-quality steel meant that the crane structure was no longer limited by the integrity of a tree trunk. The result was an explosion of innovation. Massive, steam-powered cranes began to dominate the docks of London and the railway yards of America. These weren't the tower cranes we know today, but brawny, brutish machines called jib cranes, bolted to the ground or mounted on rail cars, swinging heavy loads with a hiss of steam and a clang of metal. They dredged canals, built bridges, and loaded ships. They were the muscle of a new industrial age, but they had a critical limitation. They were largely stationary. They could build wide, but they couldn't build up. The age of the skyscraper was dawning, and it needed a new kind of giant. As the 20th century progressed, cities began to race towards the sky. Buildings like the Empire State Building were erected using derricks, a type of crane that was built on the highest completed floor of the building. As the building grew, the derrick would be disassembled, moved up a few floors, reassembled, and the process would continue. It was slow, laborious, and dangerous. The world needed a crane that was elegant, efficient, and could grow with the building it was constructing. The solution arrived in 1949 from a German inventor named Hans Liebherr. He designed and built the TK-10, the world's first mobile tower crane. It was revolutionary. It could be folded down, transported on a truck, and assembled on site in a matter of hours. This was the blueprint for the modern tower crane. Its design was a perfect marriage of strength and grace. A tall, slender mast, a long horizontal jib to carry the load, and a shorter counter jib holding massive weights to keep the whole thing perfectly balanced. It was an instant success, and the Liebherr design became the foundation for the machines that would define the look of construction for the next century. So how does a modern tower crane, a machine that looks like it should snap in the slightest breeze, lift a 20-ton steel beam without toppling over? The secret lies in a principle so simple you learned it on the playground: the seesaw. The crane is, in essence, a giant vertical seesaw. The long arm, called the jib, is where the lifting happens. The hook is on a rolling trolley that can move back and forth along the jib. The further out the trolley goes with its load, the more leverage or torque it exerts on the central mast. To counteract this, the shorter arm, the counter jib, holds an immense stack of solid concrete blocks, the counterweights. These can weigh up to 20 tons each, and they are precisely calculated to perfectly balance the weight of the jib and the maximum load the crane is designed to lift. It's a constant, delicate balancing act. When the crane lifts a heavy load far out on the jib, the counterweights ensure the center of gravity remains safely over the mast. The entire top assembly, the jib, counter jib, and the operator's cab, all sit on a massive, gear-like ring called the slewing unit, which allows the crane to rotate a full 360 degrees, powered by strong electric motors. It is breathtakingly simple physics, just executed on a scale that boggles the mind. This brings us to the ultimate magic trick. The question that started us on this journey: how does a 1,000-foot-tall crane get built? Does an even bigger crane come and build it? The answer is far more ingenious. The crane builds itself. This process, known as self-climbing or self-jacking, is one of the most brilliant feats in modern engineering. It starts with a massive concrete foundation poured deep into the ground, with the first 40 or 50 feet of the crane's mast embedded within it. From there, a mobile crane is used to assemble the rest of the crane, the slewing unit, the jib, and the counter jib, on top of this short starter mast. Now, for the magic. A special climbing frame, a large, square steel cage, is fitted around the outside of the mast, just below the slewing unit. When it's time for the crane to get taller, this climbing frame comes to life. Powerful hydraulic rams push up on the bottom of the slewing unit, lifting the entire top section of the crane, weighing hundreds of tons, up by about 20 feet. This creates a gap, an empty space in the mast between the climbing frame and the newly elevated top section. The crane operator then uses the crane itself to lift a brand new 20-foot mast section off the ground. They carefully swing it around, guide it into the gap, and a team of workers below bolts it securely into place. The hydraulic rams retract, the climbing frame lowers onto the new section, and the process is repeated. Mast section by mast section, the crane literally climbs its way up the building that it is creating. Once you understand this process, you can never look at a tower crane the same way again. It's not just a machine. It's a self-assembling organism of steel, methodically pushing itself towards the clouds. But how high can this process go? In theory, as long as the building it's constructing can support it. As cranes climb higher and higher, they can't just freestand. They would become too susceptible to wind, so every 10 to 15 floors, the crane's mast is attached to the building's concrete skeleton with massive steel collars, or ties. These ties provide lateral stability, essentially making the crane an extension of the building itself. The ultimate example of this is the construction of the world's tallest building, the Burj Khalifa in Dubai. To reach its staggering height of over 828 meters, it required 3 of the world's largest tower cranes, which eventually reached operating heights of over 700 meters, nearly 3/4 of a kilometer in the sky. At that altitude, the operators weren't just building a skyscraper. They were battling the elements in the lower atmosphere, working in a tiny glass box suspended in the void, which brings us to the human element in this story of steel and concrete. The crane operator. Their office is a small cab, often no bigger than a closet, with a singular, breathtaking view. To get to work, they don't take an elevator, they climb. They ascend a series of vertical ladders inside the crane's mast, a physically demanding journey that can take anywhere from 20 minutes to over an hour, depending on the height. Once inside, they are often alone for their entire 8 to 10 hour shift. From this perch, they control a machine of immense power with incredible finesse. Using a pair of joysticks, they can maneuver a 15-ton girder with millimeter precision, guided only by hand signals or a radio call from the ground crew hundreds of feet below. They have to account for wind, for the slight stretch in the steel cables, for the momentum of the load. It's an act that requires intense focus, nerves of steel, and an almost intuitive understanding of physics. It is one of the most isolated, yet most responsible, jobs on Earth. One wrong move, one moment of distraction, and the consequences can be catastrophic. For all their grace and engineering brilliance, we must remember that these are machines operating at the very edge of physical limits, and sometimes those limits are breached. When a tower crane fails, it isn't a simple accident. It is a city-stopping catastrophe. One of the most infamous examples occurred in Milwaukee in 1999 during the construction of a baseball stadium. A massive crane known as Big Blue, one of the largest in the world, was attempting to lift a 450-ton section of the stadium roof. Amid rising winds, the crane became unstable. With a horrifying groan of twisting metal, the entire machine collapsed, killing 3 workers and doing immense damage. The investigation later found that the crew had pushed forward with the lift, despite winds exceeding the crane's safety limits. In 2008, New York City was rocked by 2 separate, devastating tower crane collapses just 2 months apart, killing a total of 9 people. The first was caused by the failure of a worn-out sling during the self-climbing process, causing the support collar to drop and the entire top of the crane to shear off the mast and plummet to the ground. The second was traced to a cracked and poorly repaired turntable gear on the slewing unit, a tiny point of failure that led to a complete structural collapse. These incidents highlighted the critical importance of rigorous inspection and maintenance. More recently, in 2019, a crane in Seattle collapsed during disassembly. As crews were taking the mast sections apart, a premature removal of the connecting pins caused the entire top of the crane to become unstable in a gust of wind. It snapped off and crashed onto one of the city's busiest streets below, killing 4 people. These tragedies serve as a grim reminder of the immense forces at play. Failure can come from anywhere: metal fatigue, bad welds, operator error, unexpected weather, or simple shortcuts taken during the complex assembly and disassembly processes. In the wake of these disasters, the industry has placed an even greater emphasis on safety. Modern cranes are now equipped with a sophisticated suite of electronic aids. A device called a load moment indicator, or LMI, acts as the crane's brain. It constantly calculates the load weight, the angle of the jib, and the radius of the lift to ensure the crane is always operating within its safe load chart. If an operator tries to lift something too heavy or move it too far out, the LMI will sound alarms and can even lock out the controls to prevent a catastrophic overload. Anemometers constantly measure wind speed, warning the operator if it reaches a dangerous threshold, where the crane must be put into a weather vaning mode, allowing the jib to spin freely like a weather vane to minimize resistance. Limit switches prevent the hook from being raised too high into the trolley or the trolley from running off the end of the jib. And before a single bolt is turned on site, teams of engineers create detailed lift plans, choreographing every major maneuver the crane will make. It's a constant battle of engineering and procedure against the unforgiving laws of physics. So the next time you look up and see those silent sentinels dotting the skyline, you'll see them differently. You won't just see a piece of construction equipment. You'll see a legacy of engineering that stretches back to ancient Rome. You'll understand the beautiful, simple physics of the seesaw that keeps them balanced against the sky. And you'll know the secret of the ingenious magic trick that lets them climb into the clouds. You'll appreciate the quiet courage of the operator in the cab and the immense, terrifying power they hold in their hands. These cranes are more than just machines. They are a physical manifestation of our ambition, the tools we use to literally raise our world higher. They are complex, they are simple, they are graceful, and they are dangerous. They are the unsung heroes of every city on Earth. What other massive feats of engineering have you always wondered about? Let me know in the comments below. And if you found this deep dive valuable and want to understand more about the hidden mechanics of our world, make sure to subscribe and hit that notification bell. Thank you for watching.